So folks, Preet has an accomplished background, and I'm just going to share a lot of that with you. So he was the CTO of Ansys, which is now a company that, as of last week, merged with Synopsys. And he's responsible for driving the long-term technology strategy there. Prior to that, he was the CTO of Schneider Electric, CTO of ABB, managing director at Accenture, director of HP Labs, spent 20 years in academia as professor, chairman, and dean at UIUC and Northwestern. He founded 2 EDA companies, AxleChip and Banerjee. He served on the board of directors of Cray, Cubic, and Turntide, fellow of the AAS, ACM, and IEEE. He's received a BTech in electronics engineering from the Indian Institute of Technology, Kharagpur, and an MS and PhD in electrical engineering from UIUC. In addition to this, I wanted to share a little bit about AxleChip, actually. So Preet, as I was reading your book, so Preet has an amazing book called The Innovation Factory. I highly recommend you to get it. And I think if you read the book, you'll see that the Julia Hub journey has been exactly how Preet outlines companies can be built about academia, government funding, venture capital, and customers. But interestingly, in your first company, AxleChip, Preet, you built the Match compiler, which was MATLAB for FPGAs, and we see I at least see a lot of parallels with what Alan and I did back with our work, focusing MATLAB on parallel computing, and out of all of that work came out Julia. So we actually share a little bit of the path that has brought us together here. So without further ado, please clap for Preet.
Thank you very much, Viral, for welcoming me here. I'm absolutely excited to speak here today. And the topic is on digital twins, which is a very, very interesting, exciting topic, very interesting from an academic perspective, interesting from a business perspective. And originally, when I signed up, I was going to give a talk as a CTO at Ansys, but now 3 days ago, I joined the executive leadership team of Synopsys. And so I'm going to speak, so I had to change the format of my slides to Synopsys last night. So the agenda is I'm going to first talk about the Synopsys Ansys introduction, because it's a really interesting thing that is going on in the industry, and I want you to know why these 2 large companies got together, right? And then dive into the technical topic of digital twins, how it is relevant to various industries like automotive, aerospace, energy, and so on. And then go into the core technology, right? So there's 2 broad approaches, data-driven approaches and physics-driven approaches, and sort of the hybrid approach which we do. And then I'm going to talk about some of the key innovations that are going on in this general area of digital. And then I will end my talk about the future of digital engineering, which is, I hope I can get to these things, because I'm painting a picture of what's out there, right? And again, I'm honored to have people like Alan and Bob in the audience, because this is the picture that I'm painting on behalf of the Ansys, Synopsys, Dassault, Siemens. We are all actually going in that direction. So I want you all to see where the world is headed. And I will tell you upfront, Julia Hub is going to be a very, very important part of that journey. So that's basically the thing, that the future is digital twins, digital engineering, and what this community is building, Julia Hub, is going to be a most important part of that journey. So with that, let me begin with what just happened last week. So 18 months ago, year and a half ago, Synopsys, which is the leading electronic design automation company in the world with about $6 billion in revenue, decided to acquire Ansys, the leading simulation company with about $3 billion. The question is why? In the world of electronic design automation, right, when you're designing an electronic chip, like the NVIDIA's Blackwell GPU chip with 300 billion transistors, that requires electronic design automation. I mean, when I was a professor at the University of Illinois in 1985, I used to teach students how to do custom IC design, where on an IC you have masks. You have a red rectangle, which is polysilicon, and when you draw a red rectangle polysilicon over a green rectangle, which is diffusion, it forms a transistor. Those are the two mask layers that if you do it. Now, with that technology, you could design maybe 100,000 rectangles, so 10,000 transistors. So early part of VLSI design was computer-aided design. You had to design the transistors, the layouts, and the chip. Then the world of automation came in, where you essentially took standard cell designs like an 2-input NOR gate, 4-input NAND gate, and you entered your design not in drawing rectangles, but you enter it at the gate level. And then you use a automation tool like a placement tool, a routing tool to connect it up, and that's how you generate the rectangles. Then the technology went to RTL synthesis using technology like design compiler, and you say, okay, now enter it at RTL, VHDL, Verilog, languages like Julia, right? And push of a button gets the netlist of gates, push of a button gets the rectangles. And then there was high-level synthesis, which is what I did when I was at Excelchip, right? Taking high-level languages like C or Fortran or MATLAB and generate the RTL, VHDL, generate the get this and so on. So this is the world that Synopsys has been leading, right? All these semiconductor companies, the chips, when you design them from Intel, from AMD, from NVIDIA, from Broadcom, Qualcomm, so the top 200 companies that are designing chips, they use Synopsys or Cadence. Those are the two big companies that do it. So that's the world of electronic design automation. In the world of systems, when you are, I'm sure you came driving a car or flying an airplane or powered by the energy of a wind farm or a solar cell, or you are using some kind of a pacemaker, I hope not, but if you, so in all the industries like automotive, aerospace, energy, industrials, high-tech, and healthcare, that world uses, you need to design and you need to simulate. ANSYS is the leading simulation company. And so the combination is, it turns out that on a Boeing airplane, right, that is, now it is no longer only the airfoil and whatever, right? There's a lot of software that is driving the airplane stuff, right? On a Tesla car, there's 100 million lines of code on a Tesla car, right? So it's a hardware-software combination ecosystem. So the world is moving towards hardware-software systems design, right? And while Synopsys was focused on only the design of a chip, ANSYS was working on the system, bringing it together. We are now going to help customers build silicon to systems. So that is literally why Synopsys paid a lot of money, $35 billion, to acquire ANSYS last Thursday. So because of it, now essentially you have the number one EDA company, which is Synopsys. Number two is Cadence. Number three is Siemens EDA, formerly Mentor. Combined with silicon IP, when you design a Blackwell chip, right, you don't design all 300 billion transistors from scratch. You say, hey, I need a HBM design. I need a PCI Express. I need an Ethernet controller. Bob, all the technology that you built, right? These are predefined IPs. I need a GPU core. I need a CPU core. I need an ARM. All of those things you put together, right? So Synopsys is actually the number two silicon IP provider. Number one is ARM. Number two is Synopsys. And number three is Cadence. So, and when you're designing these chips, you need to have the electronic design automation, and you also need the IP. Now you combine it with systems. This is a very, very interesting combination, and it's today a $9 billion revenue company. We had our executive leadership meeting yesterday, and we are literally going to change the world to do silicon to systems. This is our vision. So in that vision, we will see that Julia will play a big role, and hopefully I'll get to that point. So now the technical part of the talk. So this is about digital twins. What is a digital twin? You have a physical asset like an airplane, right? This is the thing that is there, right? Or the engine on an airplane, or the car, or the engine in the car. Whatever is the physical asset, that's a physical asset. And then you have a digital model of that thing, right, in the digital world. And so sometimes people say, oh, a digital twin is just a simulation model. No. It is a simulation model, but that model is connected to the physical asset through, I put some sensors on that asset, right? And I collect data through an IoT platform, etc. And there's two-way information flow that happens. So you say, here is an aircraft engine. It is getting overheated. Oh my God, it's getting overheated. What if I could cool it down? I put cold water here. I do oil there. So I do all these what-if scenarios. So I do those what-if scenarios on the digital world. I say, oh, I should put a mixture of oil and vinegar or what, some random thing, right? And based on it, you make the decision, you do it, and you do it in the other part, right? That's what a digital twin is good for. And those of you who I know have watched the movie Apollo 13, that disastrous thing that happened, right? When people were stuck up there, right? NASA created a digital twin model of those things and said, oh shoot, how do I going to bring those people back? I put oil, vinegar, this, that, etc. Did all those things on the digital model. If I did this, we'll bring the astronauts back. So the concept of digital twin actually came out of NASA, right? So this that is the origin. But this is kind of what digital twins are. So digital twins allow you to track the past, deeper insights on the present, and predict the future. If we can say, this airplane is going to crash if you don't do certain stuff. This thing is, so if you could predict that with high accuracy, you can literally solve the world. So it turns out that digital twins, even though it started with NASA stuff, right, is now used in aerospace, that aircraft engine, like GE's basically they do predictive analytics of that airplane engine, right? These are normal things, you all own cars, right? You're supposed to do tire rotation every 5,000 miles or kilometers, right? Why do you do that? Because statistically speaking, if you drive your car normally, right, you're doing this, that wear and tear of the tire will be such that if you don't screw it, change it, you will have a tire burst, right? You have to do an oil change every 5,000 miles. Statistically speaking, if you don't do it, it'll mess up. But practically speaking, if you look at I drive like a madman, right? My tire, if I don't rotate it every 4,000 miles, if I don't change my oil every 2,000 miles, my car is going to explode. This digital twin on Prit's car will monitor the oil pressure, my tire things, etc., and say, hey, it's time for an oil change, time for whatever. And if I can do this accurately, instead of that $400 million airplane crashing, I will prevent that crash. So that is why having accuracy of prediction of a digital twin in aerospace, automotive, manufacturing, buildings, oil and gas is so important. Now, digital twins has been used in different phases, right? So in the product design phase, in the manufacturing phase, in operations phase. Let me give you an example. GE engines, aircraft engines. You all fly planes, Boeing planes, etc. You have those little engines there, right? The blades going around and so on. So when GE engineers design that engine, right? There are 52 blades on the engine. They have to have exactly that curve. So it's a perfect, ideal CAD model of that blade. Now you try to manufacture the blade using injection molding or whatever, that blade, which is such a beautiful picture with a circle and a spheres and so on, when you manufacture it, it's a slightly different blade, right? So now you have a digital twin in the design, ideal world. Now you manufactured it, it has all the imperfections. So every engine of GE in the actual manufactured world is slightly different, right? So literally, if you could track every one of the engines, and that's what they'll really do, with some sensors, here is how I designed it, here's how I manufactured it, I can track how that engine will work. And now this plane is an Air India plane flying from Mumbai to Ahmedabad to whatever, and it's all the suits and whatever, flying into China, doing this. So that same aircraft engine on United Airlines, only flying between San Francisco, New York, clean places versus sort of Mumbai and Beijing, right? That airplane engine is quite different after 20 years, and then a bird strikes that engine, right? So now that engine is slightly different. So in the operations phase, even though you started with a perfect ideal world of a CAD model, in the operational world, it got all messed up, right? Because there's a little bend there. So I need to predict through the digital twin, the model of that aircraft engine in the design phase, in the manufacturing phase, and so on. And you can do it beautifully through the world of simulation, powered by Julia Hub, which is where I'm getting to. So now there are these sort of two broad approaches to digital twins. One is you say, okay, here is an engine, right? And that I will put some sensors on the engine. I'll just measure the pressure, temperature, whatever, etc., on that engine, on this blade. If I could put sensors on everything, right? And collect a lot of data. And so if you collect a lot of data, it's just that time series data, pressure, temperature, etc., and you build a model. All the AI stuff that you see today, right, is basically doing that. Data-driven modeling, that approach is totally general. It doesn't care about the physics. You do structural physics, you do electromagnetic physics, you do fluids physics. Everything can be captured by data. The trouble is, so it is very general. The trouble is it requires incredible amount of data to train that model, right? Like million times of data. If you capture it, then you will predict exactly how that aircraft engine will work. The other trouble is it will only train it based on what it has seen. So if it has seen his aircraft going from San Francisco, New York, going from this to this, etc., it will never be trained to go into the streets of Mumbai with all the suit and so on, or whatever in Beijing, right? Because it has not seen that data. If it has not seen a bird strike, it will never be able to model the bird strike. But the bottom part is if you do simulation-based modeling with ANSYS mechanical, here is this model of an airplane wing. Here is a bird that struck it, right? With LS Dyna, I can model exactly how much it will bend and whether that blade got cracked or not. It's physics-based simulation. So that is, I mean, it's like the ultimate thing, right? Because physics doesn't lie, right? The world around us is governed by the laws of physics. If I say this plane is going to fly, it will fly. If Fluent says this thing is going to fly, if it's going to stall, it will stall. I mean, I kid you not, because it is so accurate, because the world is following second-order partial differential equations, Navier-Stokes equations, or Euler equations, or Maxwell's equations. That's what we do in the physics space. The trouble is, that takes a long time. You try to model a bird strike, right? This thing, bird is striking this thing, it's like 10,000 hours, right? Or should I need the result every second? I cannot. So then what you need is you take that simulation model, you have to build what is called reduced order models. Don't do the simulation at the level of the 1,000 million finite element method, but you reduce those orders from 10,000 million to 1,000 so that you can run it really fast. So there are these two broad approaches, and where we have landed is you need to do hybrid. Take the best of both worlds. Do data analytics to do the sort of easy cases, and then correct it through simulation, right? So the intuitive explanation is the following. Suppose you had a bridge, right? And there's a 6-inch crack on the bridge. Statistically speaking, of all the bridges in the world over the last 30 years, right? When you had a 6-inch crack in the bridge, within 18 months, that bridge collapsed. Statistically speaking. That's what our insurance companies, State Farm says, hey, based on all the people who are driving cars, right? If you are male, you have this risk. If you are female, you have this risk. If you are a male who is crazy like Prit, you have this risk. So they are putting it in a bucket of a risk, right? That's statistics. So that bridge with that 6-inch crack would, statistically speaking, will crack after 18 months. Now, if you could put a sensor on that crack and you monitor the crack, and now you use ANSYS simulation to do crack propagation. If I have a 6-inch crack on his bridge and I have 1,000 cars going on the bridge with all the stress strain that is going on, I will predict that crack will be 18 inches in 6 months. Pure simulation. Now I actually monitor what happened to the crack in 6 months. If the crack is 24 inches, I say, oh shoot, I have under-simulated, so I need to push it, right? Push that simulation. Or if the crack was only 12 inches, I need to under-simulate. So with simulation, I predict that, and then with the actual measurement, I bring it down. That is intuitively what is going on with hybrid. There is a lot of math with the famous professors here will know, but I'm just giving you the intuitive explanation of why hybrid digital twins work. So we have sort of put together at ANSYS, now Synopsys, this overall view of digital twin. So you have to start with the assets. The assets are the wind turbine engine, the car, the aircraft engine. You name the asset, and you put some IoT sensors on the asset. You collect a lot of data. You put it on the cloud, on AWS or Microsoft, whatever, right? Then you do data level analytics, which is what, as I said, most people, when they start doing digital twins, that's what. When I was CTO at ABB, CTO at Schneider, this is what I did to those companies, right? They have a lot of assets, robots, switches, transformers, and so on. I just created this ability platform or EcoStruxure platform, build the digital twins. So ABB could say, this robot is about to fail, and let me send a repair person to fix it, and if there is an accuracy. Then I came to ANSYS and say, hey, let's do simulation-based or hybrid, and we'll do the accuracy. So what good is this digital twin? What it is it allows you to create virtual sensors. So if you could put a sensor on every part of the blade on a G's engine, right? There's 52 blades, and all that blade, you got to put it here, here, here. You could analyze the heck out of that engine. What is going to happen? The trouble is, if you put all those sensors, that engine will not work as an engine, right? Because you're doing an invasive change in that thing, right? Or you have a large oil well, right? It's 5,000 kilometers of oil wells and so on, right? And you're putting a sensor at every meter, every inch, every whatever, right? You could do all kinds of predictions. Unfortunately, that is not real. So in the world, what you can do is you can do virtual sensors, meaning just imagine a pipe. The pipe has oil coming in from this side, and the pressure, temperature, velocity of that thing is here. Now, if I had a sensor after 1 meter, it would measure this, because through fluid simulation, I can predict, because, hey, this is a pipe, this is a fluid flow, etc., with all this turbulence and so on. It has this pressure, temperature here. If I had a sensor, this is what it would measure. But I cannot have a sensor, so I'm creating a virtual sensor. At the first meter, second meter, third meter, fourth meter, fifth meter, at the 100th meter, I actually put a sensor to say, hey, did I do it right or did I screw up? No, you screwed up, Prep. You need to correct it. So that's how you do virtual sensors. So to measure missing data, to perform what ifs, right? So here is this Apollo 13 sort of up there, screwed up, right? And how am I going to bring it down, right? I have to do, if I did this, oil and vinegar plus this, then this is going to work. So all those what if scenarios you do in the digital twin, digital world, and then based on that, I make a decision, apply. Do very accurate predictions. Hey, this bridge is going to crash. Today is Wednesday, July, whatever, 23rd. It will crash on July 28th. If you could predict that so well, my God, we could make a lot of money, because you could avoid a lot of disasters. And explore the, hey, this thing flamed. I mean, this Air India plane crashed, right? I mean, you have heard these things, right? Why did it crash? Oh, these things happened. You could literally do physics-based stuff to do all kinds of analysis, because the black box recorders have measured. Then you combine it with physics, you could do amazing things. So that's where the power of digital twins is. So now let me talk about the technology. So ANSYS has the core physics. We have the leading mechanical solver called ANSYS Mechanical or LS-DYNA. We have the leading fluid solver called Fluent. We have the leading electromagnetic solver called HFSS and Maxwell. So we take each of these physics and we can simulate it with the highest fidelity. I mean, if I say this is going to crack, it is going to crack. I tell you not, right? But it requires a 100 million finite element points, right? It will take 10,000 hours. The trouble is that is too long. So what we have in technology is we have these reduced order models. So think of if a 1 million finite element problem, right? Basically it gets resolved into sparse linear solvers. It is a 1 million by 1 million matrix with sort of some sparse elements. And now you have to solve AX equals B. That AX equals B is an order n cube computation, right, which is taking you forever. Now, looking at that matrix, you going back to your math days of numerical linear algebra, right? There are these things called eigenvalues and eigenvectors and principal eigenvectors. So on that matrix, if I were to take the most important 100 eigenvalues, the principal components, that's 100 of those. Those things are the most, I'll take those 1 million by 1 million vector matrix into a 100 by 100. Those 100 by 100 are the most important things. That's fundamentally what is going on with reduced order models, right? Now, instead of taking order n cube time order 1 million cube, I solve a order 1,000 cube, which is much easier to solve. That's basically what is going on with reduced order models. So we take all the core solvers, build the reduced order models, and do all this funky stuff with hybrid digital twins. Now we have a flow. Now within ROMs, there's all kinds of ROM technology. Again, this is just to impress you. Some of you are in the audience, hey, Preet is just not doing nonsense. There is technologies on linear ROMs, non-linear ROMs, static ROMs, dynamic ROMs. Okay, I have impressed you. So now, we have built this sort of thing, the Twin Builder. So there's just incredible amount of stuff that is going on today, and that's where Julia Hub comes in, right? So we have to take this model of a electric vehicle or a autonomous airplane or this wind farm. So these really complicated systems having hardware and software in it, right? And this combined ANSYS Synopsys stuff, right? And you have to do this model building for either brownfield applications. You have a stuff that is there, or for greenfield, right? How do you build the model? Well, I will come to that. It is actually, Julia Hub is a fantastic thing that we are looking forward to partnering with, right? Allowing reuse of existing simulation models with AI/ML. I mean, AI is actually changing the whole world with ChatGPT and others, but it is really changing the world in our area of AI/ML applied to simulation. Enabling scaled runtimes and driving a lot of ecosystem partnership with the likes of AWS, PTC, et cetera, et cetera. So there's stuff that is going on. So let me just focus on the system level simulation part. So let's say you're trying to design an electric vehicle, right? In an electric vehicle, you will have a motor, electric motor. You can actually model it in Julia, which is the high-level system-level model. Now that electric motor is powered by DC power. I have AC power. What do? I take the AC into DC, so I need some converters. Or I take a AC into DC, need an inverter. So I do all this, I'm sorry, DC to AC, need inverter. So I need a battery, I need a motor, and inverters. Then you need to have something that once the motor goes, that motor will connect with a gear, and then it will connect to the actual things, and that's how the car moves. So you could actually go in and model the motor, model all of them in Julia, and build a whole electric vehicle simulation model at a high level. But then you say, oh my God, this electric motor has these rotors and stators and all that kind of stuff. Will it really, if I apply this much voltage, my model says that torque will be this much. Is it really that much? Well, we go into Maxwell, which is ANSYS, right? And we look at the actual CAD model of the stator and the rotor and all those fantastic Maxwell's equations with all the partial differential equations, and say the torque will be 3.212. In Julia, you said 3.1. No, it's 3.212. But it required now 1,000 hours of compute to get to that accuracy, right? So in this world, what you need is you need a system-level model to do this kind of stuff, but you need to go and validate with detailed models, the 3D models. That is, and if you can bring those things, right, together, that is sort of the interesting thing. Now, in this world, for the last 100 years, 30, 40 years, the leading system-level language has been MATLAB and Simulink, right? But as you guys all know, yes, they are literally the preferred things. You go into any automotive company, they will use MATLAB Simulink as the model-based design thing, right? Then they will, after they pick that motor, then they will go into an ANSYS or a Dassault or Siemens to actually model it with the 3D. But with all the advantages that you guys are working on with Julia, right, with the compiled stuff and so on, thanks, Alan, for all the great work that you have done at MIT and the work that you guys have done in Julia Hub. This is where we at ANSYS are looking for the partnership, right? So the ANSYS Twin Builder, this system. Samir, are you here in the audience? There you go. This is the man. He is the GM for our Twin Builder. He is working closely with the Julia Hub team to say, hey, this thing can I integrate with and build this system level model, right? And which would be better than MATLAB, better than Modelica, better than all of that is sort of what we are working on. Then building all these things with raw models, scale, I actually need to speed up because I really need to cover some of the other stuff. Okay, so there is other stuff. Sorry, Samir, I'm skipping through some of that stuff because I need to. They'll catch you after for the details. So then the thing is, we are working on an ecosystem where these digital twin models, you can actually visualize it. So those of you who have seen Jensen's keynote at GTC, he talks about the Omniverse. This is this visualization platform. You have a manufacturing thing at a BMW factory, whatever. You can see all those things. So that's that powered by GPUs and so on. So what all these simulation models that we have from ANSYS, powered by Samir's twin, is now you can visualize on the Omniverse. And so you can actually have the physical asset, which is this whatever thing it is, right? Is this the electromechanical stuff. Here's the physical stuff, and you can actually see it on the Omniverse, and you can predict, hey, if this has happened, I put oil and vinegar, this is going to happen, it will show up on the picture. So imagine if NASA had this twin builder and Omniverse in whenever Apollo 13 came down, it would have done amazing things. But we are here today, and I hope there is no more Apollo disasters. Then there's this technology that Samir has been cooking on, this thing called ANSYS COSIM, right? Basically, you have a multi-physics simulation stuff, right? You have multiple things, and you have to simulate a distributed system. Some of them are with sort of continuous time, some with discrete time. It is this really complicated stuff, and so we have a technology of ANSYS COSIM, which can do this massive distributed simulation together. And I know I'm rushing up because I want to cover the future of digital engineering. So all these things happen, customers love it. Sorry, Samir, we have used it in Tata Steel, we have used it in glass manufacture, so this thing actually does work. What I really want to talk about is the future. Because this is the academic audience, right? I just want to give you a peek of where are things headed. Where it's headed is in the industrial landscape. You all know we have gone from Industry 1.0, which is mechanization, to Industry 2.0, which is electrification, Industry 3.0, which is the automation and the electronics, Industry 4.0, which is cyber physical, IoT, sensors, etc. We are in Industry 5.0, which is the AI and human and all that kind of stuff. The technologies that are pushing us in that area is AI, all the chat GPTs and clouds and Anthropics and GenAI, the blockchain, the digital twin, the metaverse. Omniverse is the NVIDIA's name for metaverse. Quantum computing, big deal, right? And 6G, right, with all the IoT connectivity. So that's kind of where things are headed from the Industry 5.0, the actual end users. So in that world, the world is moving towards, if you look at how people change from building enterprise resource planning, ERP systems, right, that was a big change that happened in the 80s, to supply chain management systems, to PLM systems, to model-based systems engineering. The world that we live in today is digital engineering ecosystem, right? So in the world of digital, I'm designing an airplane, right, with 100 million lines of C code, et cetera, and you will predict this autonomous electric airplane will fly, right? Boeing is trying to design the 787 Dreamliner set, the future versions, right? The entire thing, the specifications will come in languages like SysML, and output will be a beautiful thing that will, the airplane, right? Fully validated and will run. So in that world, this is kind of the picture of digital engineering. And if there is one picture you want to take, it is this. Yes, wow, I'll take it in with me there, right? Banerjee talking about future of digital engineering, yes. So in that world, remember I talked about the world of synthesis, right? Synopsys transformed the world of EDA to do electronic design synthesis. I mean, instead of drawing rectangles on the screen, you enter it in RTL, VHDL, Verilog, outcomes, gates, place and route, etc., and do the rectangles. That is electronic synthesis. Can we do system level synthesis? Once you do that, can you virtualize, can I validate? Can you do this with the physical assets, the IT-OT integration? Can I do the digital operations and have the embedded digital twin? So this is the whole journey, and I have one slide on each of them just to give you an example, right? So imagine I come up with a system level requirement that I need to design a Tesla beater. I'm designing an electric car that will go from 0 to 60 in 1 second and a range of 1,000 miles. I mean, if I could build that car, Tesla will be out of business. And I can, if the cost is like less than $20,000. So that's my requirement. If I could specify a requirement like that, can I synthesize a design? So if you were to work in an automotive company, right, you say, oh, I need to go for a range of 1,000 miles, right? My last car, the electric car that I had, could go only 200 miles, and I had a battery of this size. So if I have to go 3 times as much, I need a 3 times larger battery. That's how a human thinks. I need to go from 0 to 60 in 1 second, right? My previous thing that I had went from, in say, 6 seconds. So I need to go 6 times faster. That one was with the 200 horsepower battery. Now I need a 1,000 horsepower battery. That's how a human thinks. But today, the human is making every one of those steps, saying, oh, for this specification, I think you need a 1,000 horsepower motor with a whatever size battery with that gear. So the human is choosing all those steps. What if automatically I could synthesize all the stuff that is in the human's head, right? All the knowledge is captured, and this is kind of what we are working on. So you do all these things, you say, this is the EV car, and I have actually shown Viral a demo of this, right? There are 6 different designs that automatically came in. Then with Julia Hub, you are actually simulating all of those. This is one case of this combination of this electric car, which has the motor with in-wheel drive, with all the motors in all these wheels in parallel. That is going to be the architecture, right? Or it's the architecture with only front-wheel drive, rear-wheel drive. So all the choices that a human designer have done automatically, and that's system-level synthesis. The second one is virtual validation. You are designing this car, right? It is going on the streets of, driving from Los Angeles to Las Vegas, right? In the heat and so on. It's just super hard. And then the thing is going over this thing, right? So how do you actually test, virtually test, before you build that car, that it will actually work, right? So the normal way that you do is they do the unit testing. Test the motor, test the battery, test these gears and so on, and then you do physical testing, you do the combination of physical testing and so on. The future is all virtual. Because if I am saying, if the world is governed by the laws of physics, if Navier-Stokes equation doesn't lie, if Maxwell's equation doesn't lie, you don't have to build a physical prototype. Go to 0 physical prototyping, right? And we have actually done things with digital twins. The picture is, if you could show those videos, it actually shows here is a car going right from Las Vegas to whatever, really hot things over this highway, and is there overheating happening or not, right? So you could actually validate it. Then you have this IT-OT integration, right? I'm just going through this, right? You have all these different things, and you put sort of sensors, you put PLCs, et cetera, et cetera. So there's the OT part is having all this Modbus, OPC, UA, all those standards that you have. And then you connect, use all the latest Ethernet technologies developed by Bob here, right? And this is the world. The world is MQTT, broker, et cetera, et cetera. That's how, in a real system, you are actually building these things with IT-OT integration. Then you did the whole digital operations. I'm flying this airplane from New York to Kathmandu, or New York to Mumbai, right? And I will do all this thing, right? This is going this plane, et cetera. I have all the sensors. So doing this whole thing with digital missions engineering, digital twin, that's sort of digital missions engineering. The last thing is digital twin. This is kind of where somebody is headed with this stuff, right? So we did a little interesting project in this Covisa joint work, right, with companies like Bosch and all. So imagine you are driving an electric car, right? And you say it's like only 30% charged. Oh my God, if I don't find a charging station, by the time this thing goes, right, I am toast, because I am on the highway, I need a charging station. So this is called range anxiety. So let's imagine that I'm a driver and I have connected to all the power and electronics and AC and all the kind of stuff, right? On the thing says, I have to go on 30% things, and with that I could drive only 100 miles, but my charging station is like 200 miles away. What the heck do I do? If you're like me, say, oh sure, come on, turn off the lights, turn off the AC. So you do all those things, right? This thing would say, Prit, just relax. Don't turn on the lights, don't turn on the AC. You just reduce the AC from 75 to 42, and you'll be fine. And you're completely crazy. You just go in with the last amount of juice, go into a charging station, you're done. If you could predict it as well, that would be amazing. So it's an example of an embedded digital twin. I thought this was an entertaining morning. So what I talked to you about is the concept of digital twin, which can be done with pure data analytics or with simulation, and I think the world is headed towards hybrid. I am biased. I think we are well positioned. Samir and we agree on that. But the future is about this digital engineering area, and this will literally be powered by Julia Hub. I kid you not. So we are excited to work with Julia Hub and all of you in the audience. So thank you very much for your attention. Thank you.
Questions for the speaker? I'll start handing them the mic.
Yeah, thank you so much for everything that you've been, I think that we share a lot of the vision here, but what I'm really curious to hear from, your experience here is, we've put together this idea of, here's how digital twins can change the world, and it has the, pieces with IoT and simulation, What is the weakest link of this whole connection? And how should we prepare for it, right? Is it, there's a few things that come to mind. Company structures might have it so that way the people who design assets might be different than those that maintain it. Is it something with IoT security issues? Is it ability to scale simulation? Like, where in this are you looking and you go, oh, I'm scared that this is the weak link, and how should we think about what we're doing to handle that issue?
Unfortunately, it's not a simple thing with just the IoT security. It is actually a range of the things that you can cover. But I think I painted a picture that if you could do hybrid digital twins, right? So pure physics-based digital twins, even though, I work for ANSYS or Synopsys, we would like to say it just is not accurate enough because it doesn't capture the bird strike that struck this thing, right? So unless you can connect it with the data from the actual hardware, right, from the actual sensors, it will not work. So you need to do this. The difficulty here is that you have to be connected to the actual IoT structure. So I saw that you listed ASML as one of your partners, right? And Viral and I kind of talk about it, right? So let me give you a classic case of something that we are working on, right? A digital twin of a semiconductor manufacturing plant. At TSMC or Intel, right? They have these massive things with the hundreds of equipment, 5 equipment from Applied, 10 equipment from ASML, 15 from KLA Tencor, all these different equipment, right? Now, imagine if you create a digital twin of each of the equipment. In a semiconductor process, right, there's like 200 processes that you have to do. You have to do chemical vapor deposition, then you do ion implantation, et cetera, et cetera. And you do this complicated stuff, and then out comes the Blackwell chip, right? And this thing, the yield is only 1 in 100 work, right? So all the others are kind of wrong, right? And so you have a line, and you have bad stuff coming out, right? I have a yield issue. How do I fix it? So if I could come up with a digital twin of that manufacturing plant, right? I can improve if you can just improve the yield by 1%, it's like billions of dollars, right? But you can't. So, in this world, what happens is, if you could do a digital twin of an Applied equipment, and actually Applied is our customer, ASML is our customer, we can build a super accurate model of that Applied equipment, that epitaxial process, etc. Right? But to make it work with hybrid, you need the Applied sensor data to come in, and so on. Now you put the Applied equipment TSMC, they'll say, hell no, I will not let you connect the data from applied to this because this is my data, right? So the real practical stuff, I mean, the academics we know, if I could collect the data, right, it's there, but you cannot, I will not let you, right? So you have to, what we are working on a solution is to say, okay, TSMC, I kid you not, this is exactly what we are doing. TSMC, you will not let Applied have the data, but we have helped Applied build the equipment, right, with our models. So I have a digital twin of the Applied equipment and that epitaxial whatever process. Just let us have access to your data. I mean, and I will give you this thing, you do this on your stuff, and it will be so much better, right? So this is the case we are making. We are not there yet, but the challenge is this siloing of the stuff, which happens in real manufacturing. If you would crack that nut, well, it's openness and so on. People talk about openness. The real world is Applied doesn't want to because they're all competing for this thing, right? So that is the real challenge. Sorry to give a really convoluted answer, but it is really hard problem.
So that was a fantastic answer. Any other questions for the speaker?
Oh, I'm so disappointed. Nobody cares.
No.
I love it when a speaker gives a vision of the future, because that's, of course, the hardest thing to predict, as they say. So you've been a professor, you've been a technologist. As a professor myself, students often come to me, and I get the feeling that they are figuring out a course of study based on what made sense last year. Do you have any advice for students who want to look into the crystal ball and what will be most relevant a few years from now?
That's a great question. And the book that Viral referred to, right, called Innovation Factory, I am not shamelessly promoting the book. I'll just say that the thesis of that book is that large companies like ABB, Schneider, HP, Ansys, etc., right, they do a good job in the Horizon 1 innovation. I have my Fluent, what feature do I need in Fluent next year, right? That we nail it, because that's an incremental stuff, right? The adjacencies, which is Horizon 2, is sort of, yeah, I have a thing working on-prem, I want to go on the cloud, or I have a transformer in North America going to China with 220 volts. That also people know. But it's very hard for a company that is making laptops, Macintoshes, to come up with a brand new thing like an iPhone. So it takes an Apple to do those kind of stuff, right? So what I say in my book is, if companies want to do it, they really need to partner with the Allens at MIT and the startups like JuliaHub. And so this is literally what I kind of say. But in my final chapter, I say, you are all students, right? You are professors. And so when Synopsys started EDA, or ANSYS started simulation 50 years ago, the computer that I had 1 megaflops of power, had 32 megabytes of memory. So I wrote my Fortran code with column major order to do this stuff, with all these stuff, right? Based on the computing that I had at that time. And then the world of parallel computing came in. Oh, now you can do threading. So I can take my Fortran code, do shared memory threading with this. Now I did, oh, I have message passing on the Cray, so I can do MPI. So I took that Fortran code and chunk into domain decomposition, do this. And now GPUs came in. Oh, now I should take this Fortran code, now try to GPUize it. Then quantum computing came in. Now all these qubits are happening. So the real challenge that happens is you develop some product based on the technologies that were there at that time. Now, the students graduating from CMU, UP, MIT, Illinois, Georgia Tech, right? In 2025, the technologies that you have are cloud, IoT, blockchain, ChatGPT, GenAI, quantum. Now, if you say, I want to do a startup which is an EDA technology leverage with GenAI, quantum, GPUs, etc., it sounds fantastic, right? You put everything in the kitchen sink. The smart person, right, like Bob or Alan say, it's a combination of blockchain. If I took blockchain and quantum and GenAI, I did this here, that would be amazing. So think of these individual technologies as pearls. You have to create that necklace, string together those individual points, and do something like an iPhone that the world hasn't seen before. So, I mean, the iPhone technology put together a bunch of technologies, right, in a beautiful necklace. And that is what the students at MIT, you should advise them, right? You have all these amazing technologies coming, and not all of them are available. Like quantum, we are working on, I mean, I kid you not, all the technology I mentioned, I have got in the CT office working on those things, right? But my CEO says, why are you doing this? Because I don't know what the necklace is. The future of digital engineering, this system-level synthesis is actually leveraging AI, quantum, this, that, etc. That is the exciting thing for your students.
I think at MIT, it won't be the necklace, it will be the jewelry store.
I agree. Thank you. Thank you.
Thank you. I think there are a few more questions, but
I am around.
Yeah. Please do find Dr.
Take
Banerjee.
selfies with me, post them on LinkedIn. I'm just kidding.
With that, let us thank the speaker again.